That's all. Okay, cool. So welcome back, everyone. Let's get started. So in the last lecture, we started our conversation about fair division, and specifically fair division of divisible resources that you can fractionally allocate. In this lecture, we are still going to talk about fair division, but of different kinds of resources, ones which are discrete or indivisible, right? So we can no longer fractionally allocate these resources. And as you will see that this indivisibility poses a number of challenges, both in terms of how you even define fairness, as well as how you design algorithms for achieving those notions of fairness. Okay. So like I mentioned very briefly in the last lecture, there are a number of scenarios where you want to divide resources that are indivisible. For example, items of an inheritance or seats in courses at universities, public housing, as well as medical supplies. And I'm sure there are many, many more that you might be aware of as well. So just to get into the mathematical model right away. So we are going to imagine that there's a bunch of agents, okay, given by these happy triangles, and a bunch of discrete items or goods or objects or commodities, whatever you want to call them. Okay, so these are given by A, B, C, D, and E. And the preferences of agents are given by these numbers here. Okay, so the way to read this is that, say, the blue agent's value or utility for obtaining item C is 5. Right, so these are in units of happiness, and bigger numbers are better. Right. Likewise, the blue agent does not get any happiness if it is given item B. Okay. So these are values over individual items. We also need to define how agents feel when they're given bundles or sets of items. Okay. So there we are going to make the additivity assumption, just like we did in the case of cakes. Right. So here the value of an agent for a bundle or a set of items is simply the sum of its values for the individual items in that bundle. Okay, it's a fairly simplifying assumption. And an allocation of these items among the agents is just an assignment of every item to exactly one agent, right? So in this picture, I'm giving item A to the red agent, B, D, and E to the blue agent, and C to the green agent. Okay, so this is a valid allocation. Good. And again, we don't want to leave anything unallocated. Okay. Any questions? All right. Okay. And again, we can start to formalize what it means for an allocation to be fair. And again, we can appeal to one of the fairness notions that we saw in the last lecture, envy-freeness. And it means the same thing, right? So everyone is happy with what they got. Right? They don't have a desire to switch with some other agent. So for example, suppose we are given an instance of the problem like this with 2 agents and 3 items, A, B, and C. And suppose the allocation that we are given is where A is given to the red agent and B and C to the blue agent. So in this allocation, if you look from the red agent's perspective, it has a value of 4 for its own bundle. And its value for what the blue agent has is 1 plus 2 or 3. Okay, so it likes its own bundle better. Likewise, for the blue agent, if you look at it from the blue agent's perspective, from its preferences, its value for its own bundle is 5 plus 1 or 6, and its value for the other agent's bundle is just 1. So again, blue is happy with its own bundle. It doesn't have a desire to have the other agent's bundle. Right? So both agents are happy with what they have, and that's why this is an envy-free allocation. Yes? Okay. So a little bit more formally, I'm going to denote an allocation A as a tuple, as an n tuple. So if there are n agents, A1 is the bundle that agent 1 gets, A2 is the bundle that agent 2 gets, right? Each AI is a subset of items. And I'm going to call this allocation envy-free if, as in the last lecture, it's a pairwise condition. So if for every pair of agents I and k, agent I's value for its own bundle is at least as high as its value for any other agent k's bundle. Okay, same idea. All right. So envy-freeness worked very well for us in the last lecture, but as soon as the items become indivisible, I hope you can observe that envy-free solutions are no longer guaranteed to exist. Right? Imagine there's just 2 people and just one item that you want to allocate between them. Right? whoever does not get the item is going to be envious. Right? So there is no envy-free allocation, even in this very, very simple setting involving indivisible resources. Right? So right off the bat, we are having to think about what fairness even means, right? Because this kind of fairness certainly cannot be universally guaranteed. Right? But that's not where the bad news ends, unfortunately. Given an instance of the problem, so an instance of the problem is a matrix like this, like bunch of agents, items, and their values. Checking whether there exists an allocation that is NP-free, that is a hard problem. That's an NP-complete problem. Right? So not only do NP-free solutions fail to exist in some situations, even determining whether they exist or not in your given problem instance, that is also hard. Right? So both in terms of existence and computation, NP-freeness is a very demanding notion in the context of discrete resources. Okay. So as a computer scientist, whenever you see negative results like this, your Pavlovian response is to think of approximations, right? And indeed, people have thought about it. So one approximation that people have thought about in the literature is called NP-freeness up to one good, or EF1 for short. And informally, what it means is that, sure, you may have envy in the system, right? We saw that it could be unavoidable in certain scenarios, but that envy is bounded in a certain sense. Okay. Specifically, if I envy someone, then my envy should go away if I hypothetically remove one of their items. Okay. Yes, one item. So we'll see an example. Okay. So again, imagine an instance like this, okay, and a different allocation. So suppose C is given to the red agent and A and B to the blue agent. Okay. Now, note that the red agent envies the blue agent, right? Red has a value of 2 for its bundle and 4 plus 1 or 5 for the blue agent's bundle. So there's definitely envy from the red agent towards the blue agent. But that envy would go away if we just do a thought experiment where we take out the item A. Right? If the red agent imagines that suppose item A were not in blue agent's bundle, then I would the residual bundle of the blue agent. Okay. So there is envy, but it's bounded up to the removal of some item. Okay. Likewise, look at the blue agent's perspective. Right? Again, observe that it envies the red agent. But if we remove one of the items, and in fact the only item in the red agent's bundle, then envy would again go away. Right? So this is the sense in which envy is bounded. Like every agent is doing a thought experiment. And if the envy is bounded in this thought experiment, then we say that this allocation is approximately envy-free. Okay. So again, the formal definition is very similar to exact envy-freeness. Okay. So again, we are given an allocation. We say that it's envy-free up to one good, EF1. If again we have a pairwise condition for every pair of agents I and K. The only change is that now we are saying that agent I's value for its own bundle is at least as high as agent I's value for a diminished bundle of agent K, right? So up to the removal of some good in agent K's bundle. Okay. All right. So why am I so excited about this notion? Well, there's a good reason to it. That's because it fixes both problems that we saw with exact envy-freeness, right? So an EF1 allocation is guaranteed to exist, and you can actually find one using polynomial time in a polynomial time manner. Okay, so there are efficient algorithms for finding such allocations. So both in terms of existence and computation, it gives us an advantage over exact envy-freeness. Okay. Any questions so far? Yes. Better how and for whom? It may not maximize social welfare, and you can. I think it's fairly easy to see because you are imposing an additional constraint, right? You're imposing certain fairness constraint, and it's a good exercise to construct examples where, by imposing this condition, you really have to sacrifice a lot of welfare, right? Again, something that you can probably work out over a lunch break or a coffee break. But I mean, fairness does come at the cost of efficiency. Okay, where by efficiency I mean social welfare. Okay, so in one of the lectures tomorrow, I will talk about a different notion of efficiency called Pareto optimality, and then we'll see that the interplay is much more interesting. Okay, but let's just hold that question until then. Okay, yes. If both, yeah. Okay. Oh, yeah. So we are not actually removing anything. We're not destroying any items. We're just telling ourselves a story. Like, were I supposed to remove one of the items? What would happen? But I'm not actually removing anything. It's just a thought experiment. Okay, it's a hypothetical removal. So items are very much still there. Okay. Yeah. More questions? All right. Okay. So what I want to do in the rest of this lecture is basically give you a couple of ways of finding an EF1 allocation. Okay, I'll give you a couple of algorithms. One of those algorithms works in a somewhat restricted setting that I've discussed, the additive valuations assumption. And the other is actually much more general. So it doesn't even require additivity and still gives you EF1. Okay. So we are just going to talk about these two algorithms. Okay. Good. All right. Okay. So the first algorithm that I want to talk about is the round robin algorithm. Okay. I'm sure we are all familiar with what round robin means. Okay. So algorithm is pretty simple. It starts with an ordering of the agents, say A1, A2 up to AN. Just line up the agents in some way. Doesn't matter which way. And now the agents are going to take turns. Okay, they're going to come in one by one in order to pick a good each. Right. So first agent A1 comes in, picks its favorite item, goes at the end of the line. Then A2 comes in, picks its favorite remaining item, goes at the end of the line, right, and so on, until you reach AN, right? And if there are still items left, then we repeat according to the same ordering. Okay, so people just take turns, pick their favorite remaining item, and then go back at the end of the queue. Good, simple enough. All right. Okay, so just to make sure we understand, suppose the ordering of agents is red, then blue, then green. Can someone tell me what should be the allocation given by the round robin algorithm? Someone? Raise your hand. Yeah. Red first. Yeah, red's favorite item is A. So that's the highest number. So it picks that. Then blue takes up C because that's its favorite remaining item and also the favorite item, right? So that's good. Now, green's favorite item has already been taken. So yeah, either of B, D, or E it could take. So suppose E. Now B and D are left and we cycle through the same ordering again. So red comes in and what does it pick? Picks D, and of course then blue is left with an item it doesn't care about, but it has to pick because the algorithm. Okay, so you could get items that you don't care about. But that's how it works. All right. Okay, cool. Okay, so what we can show that this very, very simple algorithm can actually find a fair allocation in the sense of EF1. Okay. Anyone see the proof of this? Any ideas how to prove such a thing? So we just want to prove this statement, right? That no matter what instance of additive valuations we are given, the allocation given by the round robin procedure that we just saw, it satisfies the EF1 property that we saw a couple of slides ago. Yes. Sure, if I'm at the end of the queue, maybe someone ahead of me picked an object that I really liked. In fact, if I'm the nth agent, my top n-1 objects may have been picked for all we know. Mm-hmm. Exactly. Good. So let me just, what's your name? Parth? Okay, let me just, Parvik. Okay, yeah, so let me just repeat what Parvik said in more words and more notation. Okay, so remember EF1 was a pairwise property, right? For every pair of agents it should hold. So let's fix some pair of agents, red and blue. Okay, and let's analyze the NV of red towards blue. Okay, so now there are two cases. Either red is ahead of blue in the ordering or it is behind blue. So let's say it is ahead of blue first. Okay, so the picture looks like this. In first round, red picks something, then blue, then second round, then third round. In the last round, red might pick something, but maybe blue doesn't, right? It may or may not, depending on whether the goods are integral multiple of agents or not, right? So all those things could happen, okay? All right. So observe that from red agent's perspective, it prefers its bundle item for item over that of the blue bundle. Why? Because at this point in the first round, this item as well as this item, they were both on the table, but the red agent chose to pick this item. So it must like this item at least as much as this other item, right? It's going to draw an arrow to denote the preference of red agent, okay? By the same argument, in the second round, it likes this item at least as much as that item, and so on and so on and so on, right? Maybe there is an item in the last round with blue agent, maybe not, we don't know, okay? But item for item, red likes its bundle better, or at least as much as the blue agent's bundle. Yeah? Good? Okay. So if red is ahead of blue, then I claim that it must also like the complete bundle at least as much as the blue agent's complete bundle. Why? Because of the additivity property, right? So if you like a bundle item for item better, then as a whole also you should like it better because these things add up. Good? Yeah. So if I'm ahead of anyone in the ordering, actually I don't even have any envy towards them. Like it's envy free, not just EF1. Okay. Good. So the other case is if red is behind blue in the ordering. Okay. Right. So like Parvik was observing, okay, let's call this item picked by blue in the first round G, the good G, right? Then by the same argument, but between items in different rounds, right? Again, the red agent likes its bundle item for item better than the residual of blue's bundle, except for the removal of the stuff picked in the first round, right? Right, exactly, right? So except for this item, I don't envy it. So that's why it's EF1, because it's envy-free up to the removal of this item. Right? And because, I mean, red and blue could be any agents, this is a valid proof, okay? So we didn't make any assumptions on choosing red or blue, so this holds for every pair of agents. Good? Okay, so round robin gives us an EF1 allocation when you have additive evaluations. And you can see that we are using additivity very crucially, right? When we go from item by item comparisons to bundle by bundle comparisons, we are making use of additivity. Okay? All right. So now I want to talk about the second algorithm that I was hinting at. It's called the envy cycle elimination algorithm. But before that, let me define something called the envy graph of an allocation. Okay. So given an allocation, you can associate with it a graph. Okay. And this graph is the following. So the vertices of this graph, you can imagine as being the agents. And you draw an edge from vertex I to vertex k, or rather agent I to agent k. Okay. If agent I has envy towards agent k under the given allocation. Okay, it's just capturing envy relations. Yeah. Okay. So pictorially, suppose I'm given an allocation like this, right? So remember, C and E are going to red, and B and D to blue, and A to green. Okay. This is my allocation. How should I draw the NV graph? Well, first of all, the vertices are the three agents, red, blue, and green. Okay. What should be the edges? Yeah, so let's look at red agent's perspective. It has a value of 2 plus 2 or 4 for its own bundle. And its value for the blue agent's bundle is 1 plus 4 or 5. So there's got to be an edge from red to blue, like so. Okay, but it does not envy the green agent, right? Because it values the two bundles equally. So it does not have a strict preference for the green agent's bundle. So we don't draw an edge like that. Okay, there's no envy. It's indifferent between the two bundles. Okay, what about the blue agent's perspective? So blue agent values its own bundle at 0 plus 1. Okay, And it values the red agents bundle at 5 plus 1 or 6, and it values the green agents bundle at 1, right? So it envies red, but not green. Okay. So from the blue agent, we again have just one outgoing edge. And for the green agent, it envies red as well as blue, right? So we draw two outgoing edges from the green node. Okay. So given any allocation, we can draw an NV graph like that. Good. Yeah. Sorry, who's asking? Yeah. Yeah, that is going to be a very, very important idea in like 5 seconds. Okay, so as you rightly observed, this cycle, whenever you see a cycle in the NV graph, that gives you a signal that maybe people can swap around their bundles, right? And if I get the bundle of someone I envy, I become happier, right? So maybe that kind of operation is doing something right, and indeed it is. We'll just see that in a moment. Yeah, but that's an excellent observation. Other questions? All right. Okay. So now I'm going to talk about the algorithm, and you can see that NV cycle is right there in the name. Okay, so surely it is playing a role somewhere. So here's how this algorithm goes. It's going to make heavy use of NV cycles and NV graphs. Okay. So this algorithm iterates over the goods, right? It allocates the goods one by one. Okay. So as long as there is some unallocated good, it is going to look at the NV graph. Okay, so it's going to maintain some allocation. It's going to look at the NV graph of that allocation, and it's going to check if that graph has a source vertex. What is a source vertex? Anyone knows? And yeah, there's no incoming edge, exactly, right? So any vertex that only has possibly only has outgoing edges, but definitely no incoming edges. Good, right? What does the source vertex mean in the context of an NV graph? Right, exactly. No one envies that agent, right? So it makes sense to give a new item to that agent, right? Because if you give an item to an agent who's already envied, you're going to compound your problems, right? So if there exists an agent who's not envied by anyone, maybe it's a good candidate to give a new item, for all we know, right? So that's what a source vertex means. Okay, so if there is a source vertex, the algorithm is going to pick one of the source vertices and give the good to that agent. If there is no source vertex, okay, then there's got to exist a cycle in the NV graph, and the algorithm is going to resolve one of the NV cycles. Okay, it was going to keep resolving NV cycles until a source vertex shows up. Okay, so resolving NV cycles means that every agent that is involved in the cycle is getting the bundle of the agent that it points to, right? That it envies. Okay, so we're going to do a cyclic swap, a toggle operation, so to say. Okay. Oh, yeah. Excellent question. It will not matter today. It will matter hugely tomorrow. So when we are dealing with items that are goods, items for which you have a positive value, right? So whenever these numbers are positive, then the order does not matter. But tomorrow we will talk about a problem where these numbers could be negative. Okay, these are known as chores or tasks. There the order is very, very important. Okay, so we'll talk about it tomorrow. Yeah. Yes, yes. Yes, so that's an excellent observation. So when I mentioned the EF1 definition, that was defined in a paper in 2011, right? But magically, someone went back in the past and invented an algorithm for it 7 years before that. So how did that happen? So this paper actually gave this algorithm not in the context of EF1, but in the context of a different notion of NV freeness. Right? They did not define EF1, they defined some other notion and said that, okay, look, this algorithm satisfies this notion. Great. Right? 7 years later, someone defined EF1. And then 7 years after that, someone observed that, oh, wait, this algorithm actually satisfies EF1. Okay, hence the dates. Okay, yeah. Okay, good. Yeah, so it was a question. Pick any. Sorry? It would not matter. So you assign it to anyone. Hopefully, it will be clear that the choice would the tie breaking is not crucial. Yeah. Okay. So let's understand this algorithm on an example. Okay. So suppose our input is this. Okay, and I'm going to side by side draw the NV graph. Okay. So initially there are no edges because nothing has been allocated. Okay. Everything is on the table. Okay. Now I start allocating item A. Everything is a source vertex. So let me just assign it to the red agent. Why not? Now I have to update the NV graph, right? So as soon as I give item A to the red agent, blue and green are going to be upset, right? So that's why you have NV edges pointing this way. Okay, that means A is the red agent is no longer a source vertex. So if I have to in the next step assign item B, I definitely cannot give it to red because it's not a source. So I have to give it to either blue or green. Yeah. Okay. Thank you. Okay, everyone can hear me? Good? All right. Okay, good. So when we are assigning item B, right, we have to give it to a source vertex in the new graph, and that's got to be either blue or green. So let's say we give it to blue. Okay, and again, we need to update the NV graph, right? So for this allocation, you can convince yourselves that this is going to be the NV graph. Yeah? Okay. Now, what should I do if I have to assign item C? Is there a source in this graph? Green is the source, so let me do that and then again update the NV graph. Okay, good. Now what? Yeah, so just go in the order, right? So if the graph has a source vertex, and yes, it does, so you just give it to the vertex that is the source. Right? We only appeal to the second step if we are unable to find a source. Okay, good. So this is how the algorithm works. Okay, good. But let me not stop here. Okay, so let me continue a little bit more. Okay, although we don't need to, the algorithm is terminated, but let's sort of go one step further. Okay, so I gave D to the red node. Let me update the NV graph for this allocation. Okay, just for fun. Okay, now you can see that there is no source vertex in this graph, right? So now were there to be another item E in our problem, right? Then I will necessarily have to appeal to step number 2, right? Okay, so because there is no source, there's got to be a cycle, and there are a few cycles here, right? So there's one here, the red-blue cycle. There's the blue-green cycle, and I think green to red to blue cycle, right? Yeah. So there's multiple NV cycles in this graph. Pick any. Okay, and you can pick any now, but don't pick any tomorrow. Okay, I'm just giving an advance warning. Okay, good. So let's pick this cycle here. Okay, and let's resolve it. Meaning now the blue agent will get item C, and green will get item B, and the NV edges will get shifted accordingly. Okay, so red agent is currently envying the agent who holds item B, right? But if B is going to go to green, then it's going to, this NV edge is going to shift around. Right, remember, agents envy bundles. Agents don't envy agents. Right, so if someone else owns that bundle, your NV gets shifted. Yeah, okay. So let's do that swap. Okay, and you can observe that this is the new NV graph. And again, you can see that now we have created a source. So if there were to be an item F, we can just give it to a source and carry on. Yeah. Better in what sense? Right. So as soon as you see an NV cycle, you resolve it, even though there may be a source vertex in the graph. Okay, we could do that. Mhm. Um, so yeah, I mean, of course, you'll have to tell me better in what, like what do you want to achieve? Uh, but I don't know of anything interesting that happens if you do that. So the idea is he just does not like NV cycles, right? So whenever he sees an NV cycle, he's just going to resolve it, even if that is not needed. Even if there's a source vertex sitting elsewhere, he just hates NV cycles, so he's just going to resolve it, right? Right. So now he's wondering whether, because NV cycles are doing something right in the sense that they're making everyone happier. So the question is, well, does it provably give us something interesting, right, in terms of welfare, like some of utilities of the agents, or something? Good, good. We'll talk about that in a few seconds. Yeah, yeah. Just hold that question for a few minutes. We'll talk a lot about it. So just to sort of give a short response to your question, I don't know of anything provably interesting that happens. But again, I've not thought about this approach very seriously. So maybe it does, but I'm not sure. Yeah. Other questions? Okay. Okay. So we can give item E and carry on. Okay, cool. So I have a bunch of quick questions for you, just to make sure we understand this algorithm. And these questions are regarding the termination of the algorithm, the running time, and the fairness guarantees. Okay, so let's first try to understand if the algorithm even terminates or not, right? Because it could be that when we resolve NV cycle, we might create some other NV edges somewhere, right? And then we are caught in loop, and it might take a long, long time to finish. So it needs an argument why this approach even terminates at all. Okay. Okay. Good. So why does this algorithm terminate? Well, let's look at what this algorithm does. Right? It does two things. It either gives a good to a source vertex, or it resolves an NV cycle. These are the only two things that this algorithm does. Right? Now, the first thing cannot happen infinitely often. It can only happen as many times as there are number of goods, at most as many times. Right? Okay. So this can't be the source of the termination being a concern. So maybe this is the more interesting thing to look at. Okay. So what we can show, and what we will show, is that whenever you resolve an NV cycle, right, the total number of edges in the NV graph, that drops by at least one. The count of edges drops. So edges can get shifted around, all those things can happen, right? But the count of edges, the number of edges, goes down by at least one. And because you have n agents, you can't have more than n squared edges. So you can't resolve NV cycles forever. At some point, a source vertex must show up. Okay? Yeah. At least by one. I mean, that's all I need. It's a strict decrease. That's all I care about. Yeah. It could definitely go down by more. You're absolutely right. But for our argument, one is okay. Yeah. Okay. So this is the claim that we are going to show. Before that, suppose this claim, just assume that if this were to be true, then I think we all believe that n squared cycle resolutions are all we need. Right? So not only does this argument give us termination, it gives us a polynomial time, polynomial running time. Right? So this claim is all we need basically to show a polynomial time. Okay. All right, so let's prove that. Okay, and this would mostly be a proof by picture. Okay. So imagine a situation where you have these green vertices that are part of the NV cycle, and there's a bunch of blue vertices that are outside. Okay, so these edges are all part of the NV graph, but the dotted edges are the ones that are part of the cycle that you're resolving. Okay, and I want to argue that when you resolve this cycle, the total count of edges drops by at least 1. Right? Okay. All right. So to do that, we are going to divide the edges into 4 types. Type 1 edges are between agents that are both outside, right? So an edge from an outside agent to an outside agent. That's a type 1 edge. Type 2 edges from an outside agent to an inside agent, right? The one inside the cycle. Okay. Type 3 is in the opposite direction. And type 4 edges are between agents that are both involved in the cycle. Okay, and note that these edges need not just be the ones in the cycle, so they could be edges of this form, for all we know. Right, so type 4 edges are between only green nodes. Okay, and we'll separately analyze each type. And we'll argue that, first of all, for any type, the number of edges of the type don't go up. And for some type, they definitely go down by at least 1. Okay, all right. So what about type 1? Can the number of type 1 edges grow? Exactly, right? These edges are unaffected because why? Their bundles are static, right? Nothing is changing here. So if there was NV, there is still NV. If there wasn't any NV, there still isn't any NV. Right? Nothing is happening. It's the boring part of the algorithm. Okay. All right. Okay. What about type 2? Exactly. Right. So these edges get shifted. Why? Because initially, this agent was holding a bundle. Now, when we resolve the cycle, that bundle comes up here. Right? It's given to the agent who envies it. So if I am the blue node, if I envied that bundle, now my envy edge just gets moved around here. Right? Okay. Good. So the count of such edges will not change. Good. Okay. So far, we are not violating the lemma. That's good. Okay. Good. So what about type 3? May go up, go away. Exactly. Right? So these kind of edges, they could either stay or they could disappear. But for a fact, no such new edges will appear. Why? Because say I am the green agent, right? Because I'm part of the cycle, I'm becoming happier. Right? This agent's bundle was where it is, it's unchanged. Now, because I'm becoming happier, my envy for that other agent might either still be there or it will go away. But it certainly does not increase. Right? So these kind of edges can either stay or, I mean, even if they stay, the envy magnitude drops a little bit, or they can completely go away so that there is no envy. Okay? But the count certainly does not go up. Okay? So I haven't still proven to you that the count strictly goes down. That's going to come up in the next step with type 4 edges. Okay? So far, type 1, 2, and 3, they could either stay the same or go down. We don't know. Okay? But for type 4, they must decrease in count. Can anyone tell me why? Okay. Not all. Exactly. Right? So type 4 edges could either be of this form, right? And when you do that, they will go away, right? But they could also be type 4 edges of this form, right? That are not to your neighbor in the NV cycle, right? These edges will just get moved around, right? They might either disappear or move around. But for a fact, at least the edges in the cycle, they are going to be absorbed and they're going to go away. Yeah? Okay. So you might need to maybe go back and stare at this picture for a few seconds, but that's sort of the high level idea, why the count must strictly drop. Yes. Can you speak up a bit? Yes. So good, good. So where could such an edge come from? Think about it. So I mean, if by new edges being created, you mean uh, there's no edge here right now between these two diagonal nodes, but now there is by virtue of an old edge being shifted here. That can happen. But I'm saying the count of the edges must drop. The total number of edges must drop. So edges can get shifted around. You could see edges appearing where there weren't any before, but the total number must strictly drop. Exactly. So at least that edge is definitely gone. Other edges get either shifted around or they disappear. Okay. Okay. Um, I don't know if it is provably faster. Maybe one could create examples where it takes pretty much as long. That's my hunch, but I'll have to, off the top of my head, I don't know of any examples, but maybe if we think about it. Yeah, so there is some. I've seen a paper that looks at implementation of this algorithm. They're trying to make it faster, right? By carefully choosing cycles, but that's still at the level of heuristics. Rather, it's not a provably faster algorithm, so to say. But I think in practice you could use things like the ones you're suggesting. So choose cycles carefully so that you don't have to resolve too many cycles down the line. Yeah, yeah. Yes. Good. So that's coming up, right? So I'll argue that this algorithm uh, gives you EF1, and from that argument, hopefully you can see that we are not using additivity very crucially. Yeah, good. Thanks for reminding me. Yeah. Other questions? Okay. Okay. Cool. So I hope everyone is convinced that the algorithm terminates. Yeah. Okay. For the same reason, you can actually get termination in polytime. Okay. So let's argue the more important thing. Why is this allocation fair? Right? Okay. So why does it give EF1? Well, again, let's remind us of EF1, right? So EF1 says VI of AI is at least VI of a subset of agent case bundle. Okay. Okay. So the high level idea here is that every iteration of this algorithm, it preserves EF1. By preserves, I mean that if the partial allocation, so partial allocation is an allocation of a subset of items, right? So some things have been assigned, some others are on the table. If that partial allocation at the beginning of an iteration satisfied EF1, then it will continue to satisfy EF1 after the iteration. Okay, so if every step you maintain EF1, the final product should also be EF1. So it suffices to show this. Okay, so let's recall what the algorithm was doing. Here's the pseudocode. Okay, it was doing two things, either the source vertex assignment or resolution of NV cycles. Okay, okay. So if you assign an item to a source vertex, okay, okay, and here's the definition of source vertex, by the way. So no agent NVs the source, right? If S is the source and I am agent I value my bundle at least as much as the bundle of that agent. Okay. Now suppose I give good G to the source, then this condition holds, right? So AS union G is the new bundle of the source, but up to the hypothetical removal of the same good G, I don't envy that bundle, right? Because of this condition here, because it was a source, right? So that's why giving a good to a source maintains EF1, right? Because you did not envy the source, so up to the removal of the newly assigned good, it's definitely envy free. Good, all right. So this step preserves EF1. What about NV cycles? So here again, one can give a sort of a hand wavy proof by picture. Okay. Why does resolution of a cycle preserve EF1? Okay. Um, well, if you, again, these were the outsider agents. If you look at their perspective, right? From their perspective, so say I'm one of these agents, right? I may have envy towards some of these green agents, I may not. Okay. But my envy was bounded to begin with, right? Remember, before the iteration started, we assumed we had an EF1 partial allocation, right? Now, after we resolve the envy cycle, note that we are not breaking the bundles, right? We are just completely switching the entire bundle from one person to another, right? So if there was an item in the bundle that offset your envy, that item is still there, right? It's just that the owner of that bundle has changed, right? So if your envy was bounded towards a bundle, it continues to be bounded. It's just that the owner of that bundle is some other person, right? So from the perspective of these agents, EF1 is preserved. Yes? Okay. What about the green agents? So for the green agents, again, two things are happening. One, every agent here is strictly better off, right? So the VI of AI term is only getting better. And if I envied some bundle, again, that bundle is just changing hands. So if my envy was bounded towards the bundle, it's still bounded, and it might actually go away, for all we know. So for the same reason, EF1 is maintained even from the perspective of the green agents. Yes? Okay. And I hope you can observe that nowhere we are appealing to additivity. All we are using is that adding a good to a bundle only makes it better. Right? This is the monotonicity condition. Okay. So because we did not use additivity, what we can argue is that for monotone valuations, not just additive, NV cycle elimination gives us EF1. Okay. So additive is a very small subclass. Monotonicity is a much, monotone valuations are a much broader class. And this NV cycle based idea gives us EF1 even for this big class. Okay, round robin only worked in this little yoke here, but NV cycle works all throughout. Yeah? Okay. So let me just stop here. Okay, this is the reference for the NV cycle elimination algorithm. And tomorrow we are going to talk about a stronger fairness notion. Okay, so right now we talked about EF1, NV free up to some item. Tomorrow we are going to talk about something called EFX, which is NV free up to any item. Right? So I should not envy you even up to the removal of my least valued item in your bundle, not the most valued one. Okay, and that turns out to be a much more complicated fairness notion. So see you tomorrow. Yeah. Yes. Yes, it's an invariant, yeah. Yes, 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 yes. You could, so you could give a bundle of stuff as long as you do it to different sources. Yeah, that then you might risk losing your invariant. Yeah, yeah, that's important. That's important. Yeah, yeah. Unless your goal is NV free up to K goods. Yeah. So yes, any cycle resolution is a Pareto improvement. Yes. Exactly, exactly. So you Pareto improve the current partial allocation, but if you choose resolution, maybe your trajectory of very different and the allocation you end up with, it's not clear if it's Pareto dominating. Yeah, yeah. But just as an immediate measure, if you want to resolve NV cycle, that's a Pareto improvement. Yes, good. So that's lecture number 5, the research direction section. We will talk about that. Yeah, thanks. Excellent question. Yeah. Yes. Oh, yeah. Anyone? Yeah.
Okay, so we'll next meet at 2:30 for the next lecture.